Hey everyone, welcome back to Matthew 61. This is Scott. Let's get started. Now, what we are going to do is follow up on the last section, and we are going to begin what is going to be an epic theorem that's going to ultimately have like 20 different parts, I think, to it, that will give us a very comprehensive view of what it means to be an invertible matrix. So this is 2.3, Characterizations of Invertible Matrices. Characterizations of invertible matrices. Alright, so what we're going to do right now is just peel off the band-aid and get to work. So here is a theorem, and this one, unlike most theorems, which I don't usually dignify with names, this one we will give a name to. We will christen it the invertible matrix theorem. But we'll be building onto this over the course of the course, and so let's call this the Invertible Matrix Theorem, Volume 1. Alright, so here's the setup here. We are going to be talking about an n by n matrix, so a square matrix. Anytime the word invertible is in play, unless you have some reason to suspect otherwise, you should always assume that we're talking about a square matrix. The question of invertibility doesn't even quite make sense if it's not a square matrix. There is such a thing as what is called left invertibility and right invertibility, but that's not the subject of this class. When we say invertible, we mean full-on two-sided invertibility, and so this is only even an option if the matrix is a square matrix. So the setup here, A is n by n, in other words, square. So in this situation, the following so I should say then. So that's a setup, and under those conditions, the following are equivalent. And when I say equivalent, I mean logically equivalent, which means that if any one of them is true, any other of them is also true. If any one of them is false, any other of them is also false. So if any is true, all are true. If any is false, all are false. Okay, here we go. So the first of, in this dose, we're going to have 10 conditions. 10 conditions that are all going to be equivalent effectively to this one. So A is invertible. We can also say, by the way, A inverse exists, would be another way of wording this. Or A is non-singular. Depending on how we want to think about things, these are different ways of wording the same fact. Okay, so A is invertible. Well, let's think about what that means. So A is invertible. Now, if you think back to the last section, we have a technique for finding an inverse to a matrix, and that involves doing row reduction. You set up a matrix on one side, you set up the identity on the other, you row reduce, and if you can get the identity on the left, then what's on the right will be the inverse. So if A really does have an inverse, that must mean that the stuff on the left row reduced to make the identity. So in other words, A is row equivalent to the identity matrix. And here the identity matrix is the n by n identity because we are talking about n by n matrices. But wait, what does that mean? So the identity matrix, so remember. Alright everyone, I'm going to pause the video for just 1 second because as you can tell my pen is running out of ink. Here's a little peek behind the scenes. It has this converter in here and it is empty. So let me go refill that and I'll be right back. Alright everyone, we're back in business. As you can see, my pen now has ink in it. So we can proceed. Maybe someday I'll open up a Patreon and my patrons can receive exclusive access to bonus content such as watching me fill up my fountain pen. But in the meantime, back to work. So remember, the identity matrix just means like 1, 0, 0. Let's say I3, just for example. 0, 1, 0, 0, 0, 1, for example. So we would have to be able to row reduce down to the identity. But wait, what does that mean? Well, if we think about the row reduction, this is the ultimate in RREF. It's got leading ones in every row, every column, which means that it has all n pivot positions. So we could say A has n pivot positions. Another way of wording this is it has full rank. You'll see more what that means later on, but I just want to give you all the words. So A has full rank. But wait, let's think more about this. Let's say that we were to augment A by the zero vector. So that would mean that would be equivalent to solving the homogeneous vector or matrix equation, I should say. Ax equals the 0 vector. Now, when you augment by zeros, all the row operations you do are just going to be adding and subtracting multiples of 0 to 0 on the right column, which means that we would end up row reducing it down to just get this augmented by things that always stayed 0. We maybe scaled them up, scaled them down, but they never stopped being 0, not for a second. So that would mean that our solution would be x1 equals 0, x2 equals 0, x3 equals 0, meaning in the language of homogeneous systems of equations, this has only the trivial solution. Which means, in other words, that x is the 0 vector. But wait, what does that mean? That means that if we think of x as being combinations of the columns of A, so we can think of x as being the weights of the different columns of A, this means that there is no combination of the columns of A that equals the 0 vector, except the combination that is 0, 0, 0, 0. So this means that the columns of A are linearly independent. So columns of A are linearly independent. But another thing we can say is that AX equals B. So in other words, by the way, this means no column is redundant. All of the columns play some part that is irreplaceable. So this means also, so this is actually not a direct consequence of the preceding one, but it's a consequence of being invertible. So now we're picking up a different thread. AX equals B has a solution, in fact has a unique solution for all B in Rn. This was a consequence we saw in the last section, and in particular, we could even say what this solution would be. It's what you get when you cancel the A by multiplying by A inverse. Now, another way of wording that, based again on thinking of the x's as being a recipe for linear combinations of the columns of A, this means then that the columns of A span Rn, which means, in other words, every vector in Rn is in the span of the columns of A. Any vector of Rn is in the span of the columns of A, i.e., is a linear combination. Of those columns. So that's just rewording that. Now, H and I, so the next two parts of this are actually kind of trivial. They're pretty trivial results, but we're just putting them in the record. So there exists, or there is, an n by n matrix C such that CA equals the identity, and furthermore, actually, not and furthermore. So, scratch that and furthermore remark. I'll just say that as the next part. There is an n by n matrix D such that AD equals I, and now the and furthermore. And furthermore, C equals D, which equals A inverse. So here's where this actually becomes a little bit less trivial. So what I'm really saying here is the inverse works on both sides. It is the same from both directions, and it is the only matrix from both directions that will do this. So C and D must in fact be the same thing, and they must equal the inverse. So there's no such thing as a one-sided inverse for a square matrix. If it works on one side, he works on the other. That's really the content here. So in other words, for a square matrix, all inverses are two-sided. So I should just say that as well. So for square matrices, all inverses are two-sided. So that's what really this is saying. And that itself is actually a little bit of a surprising and interesting fact, because it is not the case that the matrix multiplication is commutative, and so therefore it is a result worth putting in the record. That matrix inversion actually produces a result that works on both sides. And then the last one is A transpose is invertible. Now, that's the end of this theorem. And the use of this theorem is that if you want to say that a matrix is invertible, which is going to be our first task of this, we just need to show that any single one of these things is true. So if any single one of these things turns out to be true, then we know the matrix is invertible. So using this. If any of the above is found to be true, we can know that the matrix is invertible. So let's take this for a test drive here. So as an example, using as few steps as possible, determine whether each of the following is invertible. All right, let's go first with this. Let's do a 3 by 3. 1, 2, 3, 0, 4, 5, 0, 0, 6. All right, and I'll just say A equals that. So we have something to refer to. So A equals this thing. Invertible or not invertible? Well, thinking about it, the question here is which of these would be easiest to use. And looking at it, if you look at C, it has n pivot positions. We can be sure of that. Even without doing the scaling and getting the fractions and whatnot, I know where my pivots are going to lie here. We've got this already in echelon form. It may not be reduced, but it is in echelon form, which means I know that there are pivots here, here, and here, or at least pivot positions. So it has n pivot positions. So therefore, by the way, I'm going to use a standard logical abbreviation for therefore. It's a little triangle of dots. In case you've never seen it, here it is in the record. Therefore, by C, A is invertible. Alright, now let's look at another example. And if you look at matrix A, which is what we call upper triangular, meaning all of the non-zero entries are on or above the main diagonal, then we can see that that implies that the matrix is invertible, because that gives you, as long as there are non-zero entries along the main diagonal here, that gives you pivots right where you need them to be. Let's see what would be the case if what we had was a matrix that was, as we say, lower triangular. So that means a 0 here, 0 here, and a 0 here, and then all the non-zero entries are on or below the main diagonal. So let's say we had 1, we had 3, we had 2, we had -1, we had 5, and we had 7. Now right here, it wouldn't be too hard to do enough row reduction and whatnot in order to try to figure out what the deal is going to be with the pivots of this. And in fact, it would turn out to be a pretty straightforward row reduction. But this has as few steps as possible, and so there's got to be a backdoor. Now, looking at this versus this, we don't as yet have a clear vision of what the pivots of this would be. But if we think about the properties above, and in particular that last one, a transpose is just as invertible as the original matrix was. So if we think about this in relation to this, the transpose of this would be of a very similar shape. In particular, 1, 0, 0 would now be the first column, 3, 2, 0 would then be the second column, and -1, 5, and 7 would be the third column. And what we have now is an orientation that puts us very, very comfortably in the same situation as what we had before. So by part C of the theorem, we can say that that A transpose is definitely invertible, and then therefore by part J, we can say that A is invertible. So by part C, A transpose is invertible. Therefore, by part J, A is invertible. A transpose and the original matrix are equally invertible. If one is, the other is. If one is not, the other is not. Okay, so we've had here two examples of triangular matrices, one upper triangular, one lower triangular, and have discovered that we had some easy way to determine the pivots and therefore some easy way to determine the invertibility. Let's now take a different case. Let's take a matrix A which equals 1, 2, 3, 0, 0, 0, 4, 5, 6. So here we have a matrix where something immediately jumps out at us, and that would be the second column. So the part of this matrix that is remarkable is that column right there. And now let's look over our theorem and see what it has to say about columns and see what we can find that would be relevant here. So the first mention of columns here is part E. The columns are supposed to be linearly independent in order to have an invertible matrix. Here we've got a column of all zeros. If you've got a zero vector in your set, then that actually is a case closed matter of linear dependence. So that means, because of the zeros, the columns of A are linearly they're linearly dependent, which means because this theorem works both ways, if they're all true together, they're also all false together. That means that, so therefore, by part E, A is not invertible. So this is just a short little sample of the ways that we can make snap judgments as to whether matrices are or are not invertible without having to go through the process of row reduction. As the term progresses, we'll find more and more conditions that are also equivalent to this same condition of invertibility, and we'll add more and more parts to a growing epic theorem. So the invertible matrix theorem, we'll be adding more and more parts to it. We've already got 10, and the parts will just grow and grow and grow over the course of the course. So to learn more, stay tuned, and I'll see you in the next episode of Math 261. Till then, bye.